All right, so I have one formula for substitution. I have a formula for weight.
mg.
Yep. And so I have tension 1 is equal to mg. And that's the primary shortcut. In a problem like this, I know immediately that the tension in this rope number 1 has to be equal to the weight of the box, given its in static equilibrium. And so the shortcut would be just going ahead and putting the W right here. So technically, it's a tension right here. And now solve.
Wait, I'm sorry, could you say that last piece? I didn't quite follow what you said.
I knew that the weight and the tension tension 1 had to be the same.
Right.
And so the shortcut is, I could have skipped that step and just gone ahead and just acknowledge that this is equal to the weight of the box.
Oh,
In which case, I'd already have a W right there. Or mg if I want to take another shortcut. All right, so now we are left with, well, let me plug that in there. So we have tension 3. Now, the more I write, the more chances I am going to make a mistake. So what I'm going to do is I'm going to use A for tension 3 and B for tension 2. You don't have to. I'm just doing this because I don't feel like writing as much. A cosine 50 degrees minus B cosine 30 degrees equals 0. And then tension 2, so that B sine of 30 degrees plus A sine of 50 degrees is equal to mg. Take a moment to convince yourself that I did not make a mistake in math.
I'm confused where force tension 1 went in that second equation.
Tension 1 is equal to mg, so I went ahead and made that substitution.
Right.
And then I took my two negatives here and I added them to both sides. And then I just flipped the order in which I wrote it.
Got it, okay.
Two equations, two unknowns. I still have written as mg right there. We could go ahead and do the 5 times, let's assume it's Earth. Let's go ahead and make that official. Earth. Generic place on. And so that's going to be equal to 49 newtons. So how do you solve it? What can I erase? So I'm going to put that. Trusting everybody has this at this point. All right, how do you solve?
How did you get to 49?
mg. Are you good where the mg comes from?
Yes.
All right, the mass is 5 kilograms, and g, since it's some generic place on Earth, is 9.8 meters per second squared.
So we need to isolate either A or B and then plug that into the other equation?
That's one way of doing it, okay? Which A do you want to A or B do you want to isolate? I have 2 A's and 2 B's.
Maybe we should isolate the A in the first equation,
Okay.
since the other one has a number.
So A is equal to B cosine 30 degrees divided by cosine of 50 degrees. take a moment to convince yourself I did not make a Carroll's error, or to convince yourself that I did, and let me know.
That seems right.
And so plugging that into the second equation, I have b sine 30 degrees plus b cosine 30 degrees over cosine of 50 degrees times sine of 50 degrees is equal to 49. Now what?
We divide 49 by that big massive everything. Or maybe it makes sense to just divide it by the pieces that are multiplied and then just, I don't know. So would it be 49 over sine of 30 degrees plus b cosine 30 divided by cosine 50 times sine 50? Just to isolate.
If you isolate one b, the way you said it.
You're right, you're right. I don't remember.
Would you divide by just the sine 50 at the end?
Divide by what again?
Or, no, I guess.
Oh, you said sine 50.
Yeah.
No, because that would put a sine 50 here and a sine 50 here.
Okay.
It still doesn't. We need to somehow isolate the b's. Once again, we are answering the question from math class of when do we ever have to know how do you do this? Now.
Is this a distributive property thing? I know we've done that in these types of problems before.
The flip of that, what's the opposite of distributed?
Factoring?
Yes.
Right.
You factor. We have a b here and a b here. They're both linear. They're both the same. There's no square involved or anything like that. So you factor it out. So I'm left with b times sine of 30 degrees plus, I guess that's cosine of 30 degrees over cosine of 50 degrees times sine of 50 degrees equals 49. Now I have a single b in my equation. And what's the last step? Or next to last step, depending on how you want to.
49 over everything in the parentheses.
Yes. We divide by that. And we get some magical number here.
Well, gosh, it better be magical at this point.
A number that you will be telling tales of for generations to come. I was there, figured out what B. All right, just, I can wing it here. See how close I get. Bless you.
Thank you.
Well, people are doing a calculator, you see, if I want to change any of that.
Well, I completely forgot what it is this number is going to be.
But one step at a time, let's do the math first.
Did anyone else get 31.98? No.
No.
Yes.
Oh. That's not 4.9, but 49.
Yeah, I was wondering where you were getting that from.
All right, so anyway, there I am correcting it when it's third. What is the actual answer?
31.98.
Units?
Uh,
Now we get back to what does this actually mean?
force tension two, so, yeah, I guess it'd be newtons.
Anyone get a number different from 31.98 that you wish to stand up and go, I don't know what happened in your childhood, but it was wrong?
I got 34.6.
Which rounds off to 35. I think you
I feel like I probably made a mistake, but let me read.
got 34.6.
Yes.
Anyone else get either of them? Yes, Freddie, you're doing this in your head. What'd you get?
I don't know.
And if you translate that, that translates into, he got 35 also.
Okay, I got 31.98 the second time I did it.
All right. All right, so we have our value for B, that's the tension in rope 2. And now for the tension in rope 3. Well, we have a formula right there once we know what B is. Oh, Dan?
So for, B is 49 divided by the equation, and that's 31.98,
Yeah, so 49 divided by whatever that is right there.
it's 31.
3 people are saying it's 31.98.
Can I ask a question about the, factoring? I feel like that's the part I'm getting a little hung up on.
From here to here?
Yeah, I just feel like if you're pulling B out, it seems that you would also have to pull B out of some of the other pieces, like the cosine 50 or the sine 50. It's just an algebra issue that I feel like.
If you distributed, you multiply, so let's first on the language, factors and terms. Terms are added and subtracted, factors are multiplied and divided. So when you distribute, you multiply whatever's on the outside by each term. So it would be B times sine 30 degrees and then B times that whole bit. Since
Right.
that whole thing is one term,
Right.
and so it's just reverse of that process.
I see, okay.
Okay.
Got it, thank you.
All right, so A, do we have someone work that one out?
I got 43.09.
.09?
I already rounded it.
Yeah. The pause there is not for,
Oh, I'm sorry, Newton.
thank you. So what we ultimately have is the tension in this rope right here, rope 3, is 43.09 newtons. The tension in this rope right here is 31.98 newtons, and the tension in this rope here is 49 newtons. Does this make any sense whatsoever? So first off, before we answer that question, let's start out with, are there any other questions about how we came upon those numbers? Hopefully it doesn't involve something that I've erased, but if it does, we can reproduce. Any questions up to here? Eric?
This is backtracking kind of, but when you did FT1 minus FT2 sine 30 minus FT3, why is there a minus sign there between?
Here and here?
I know why it's FT1 minus that, but then why is there a minus between FT2 sine 30 and FT3 sine 50? Like, why would this not be?
Why do you think it should be a plus sign?
Because they're both in the same direction, right, going in the.
Which would be my argument also. All right, so I'm going to make an assumption here about the way you're thinking about it, and just correct me if I missed that.
Okay.
And I apologize if I cut you off.
No, that's fine.
All right. There are two ways of actually setting up these equations. So let's just simplify it. I'm gonna simplify it down into, I've got force M, force N, and force P. So if down is positive, one of these is gonna work. Yeah. So if down is positive, I take all my forces in the positive direction, and then I subtract the ones in the negative direction. Equals MA. this is typically the way I do it. What I've seen some students do, which made me think this is the way you're thinking about it, since these are going in the same direction, I could have also written it as M is down minus P plus N is equal to MA,
Yes.
and doing it that way.
Yeah.
With the parentheses there, once I distribute the minus sign, I basically get that.
Get that, okay,
Absolutely nothing wrong with this, just don't forget the parentheses.
okay.
Okay. Did I?
That answered my question.
Okay.
Yeah, so, in our, second equation, why did it equal mg? Like, I thought acceleration was 0.
It is, all right, so I'm starting here. I know that from the third equation that the tension is equal to mg. This tension has to be equal to the weight, because the difference is 0. So I make that substitution, so I have mg minus this minus that. I want to keep that, we'll get rid of the earth. So the next step is, I'm gonna isolate mg, because that's an actual number, so I'm just gonna bring the constant over to one side. So the way you do it is, well, I add those to the other side. I put something on one side of the equation to the other, one side of the equal sign to the other, by just undoing what's ever attaching it. It's attached by a negative sign, so I add. So I'm left with mg equals tension 2 sine 30 degrees plus tension 3 sine 50 degrees. And then when I wrote it over there, I just wrote this side first and then I wrote that side.
Okay, but, so then, why did one of them have to equal 49, like?
For this specific problem, the total force is equal to 0, just as you said. In this particular problem, mg happens to be equal to 49.
Okay.
Because my mass was 5 kilograms and g is 9.8 meters per second squared.
Can I offer something that made me figure that out?
Oh, yeah.
So mg and ma, I feel like I didn't understand the difference between acceleration and acceleration due to gravity until this class. And so ma was equal to 0 in these two equations because the acceleration of the box was 0. But the acceleration due to gravity, which is what the mg is, which we subbed in for w. So it looks the same, the like big long equation with mg at the end. But that was just from substitution. And that one is equal, the acceleration due to gravity still exists. I don't know if that helps.
And that's the 9.8, right?
Right.
Okay. That actually really helps.
Okay, good.
Okay.
It took, yeah, I couldn't figure that out before for a while. That's why, for when I write it in my notes, I always put M and 0 or A, you know, like, I always include those because it confuses me. Right.
That's what Anna wants.
Well, wow, sorry.
Another correct response is, yes, that is what I want.
Yes, that is what I want, thank you.
Other questions up to here? Now let's talk about if this thing makes any sense whatsoever. The greatest tension obviously is the one down here. This 43.09 newtons, obviously, rope 3 has a greater tension than rope 2. Why does it make sense, and it does, that rope 3 would be bigger than rope 2?
Because the rope is closer to a vertical angle?
Absolutely. Because if this were straight up and down, it would be taking the entire brunt of this, and it would be 49 newtons. And so the farther I get away from it, the lower it gets. And this one is much further off of the vertical than this one is.
So basically, if the box was hanging straight from what would be, whatever the one on the right is, I forget which one we assigned that to, but, or whatever the other one is, the one on the right, that's
Oh,
supposed
right.
to be vertical.
The-
So if that were vertical, the one on the left would basically just be stabilizing it, but it wouldn't be taking up any of the tension if that right one.
Right, I mean, ideally, the tension would be zero,
Right,
stabilization only, I guess stabilization, the fact that if it moved, it would break.
yeah, it would break it, but yeah, okay, that makes sense.
The classic static equilibrium problem. Can't remember if there's a master set problem. There was a long complicated, well, complicated if you mess up the force diagram, then yeah, it was impossible. There's a problem on a test years ago where everything was nice and rectilinear, all the forces were vertical or horizontal, except for there was a rope, and two of the ropes were horizontal. One was horizontal, one was vertical, and I had one at an angle. But if you miss the connection point as being a point where you have to do a force diagram, then it'd be very difficult to solve.
Related to that question about the angled ropes, I wonder then if this rope on the right were on some kind of pulley, a pulley system was, or not a pulley system, but a slider was implemented partway through the problem, and then moved over to the middle, and then reattached to the wall, so it is straight down on the box, but you still have this other rope at 30 degrees. Would you no longer include any force tension on this rope because the vertical rope is taking all of the weight of the box?
If you did that, I mean, conceptually, if you saw it conceptually, yeah, you could say, well, that's not doing anything, I'm just gonna ignore it. It has no mass whatsoever, so it really doesn't, it's there for decoration, or stability if a side wind comes up. Mathematically, let's say you don't see that. So mathematically, what would happen is, so rope 3 is straight up and down, so this is now, it'd be instead of cosine of 50 degrees, it'd be cosine of 90 degrees. So that term would drop away. Or let me just go ahead and FT3 cosine of 90 degrees.
Yeah, just.
And
Yeah.
This becomes 90 degrees. But in the first equation, cosine of 90 degrees is a quiet zero there, so this term would drop out. And you're left with tension 2 times cosine of 30 degrees equals 0. So tension 2 would have to be 0.
Got it.
Look at that.
Yeah, that makes sense.
The beautiful way that physics stabilizes like that rope does. Other questions? Or same questions that don't feel like you have to ask a new one? All right, at this point, it's all just more of the same. I don't do anything with drag. Elasticity, I don't do anything with, although we do touch on, I guess we deal with elasticity, slightly different version in a later chapter, but the chapter 5 version of elasticity is not something I deal with in 151. Unless we got loads of extra time, and I don't expect we'll have loads of extra time at the end. So that means we need a new sheet so that we can actually have things due. Woo! Stuff to hand in. Meanwhile, those of you who are watching this on video, just imagine what's happening right now. or presumably, this video will be watched for years to come, 100 years from when it's filmed, people will still be watching this. And just imagine how many people in this room are now dead. Sorry about that. Today is the 15th. Oh. And if you, put an extension in to do taxes, get an extension on filing taxes, today's the deadline. Alright, so that's 15. 18. 20. Alright, so let's say there's, I think for 151, I've got master set 4.5 concept and master set 4.5 application. So I don't think I have it split chapter 4 and chapter 5. So the master set 4.5 application. If it turns out that I do have a chapter 4 master set and chapter 5 master set, and I've just had a moment, it's the chapter 4 one. Oh, this is the 20th Newton's second law lab due. 3 weeks after the fact. But run into issue with, I am gonna do the quiz on chapter 4 on the same day as the master set is due. So, plan your lives accordingly. The following Friday, quiz on chapter 5, and then master set 4, 5. Oh, sorry, I said application there. The first one should have been concept. Application is next. And the quiz on chapter 5 the following Friday.
So the concept and the application master sets are 2 different things?
Yes,
Okay.
I believe so.
And what does it say on the 20th?
The N2L lab due, the Newton second law lab, the one that we did a couple weeks ago.
Yeah.
I usually don't write when labs are due on there, I don't think I did that on the other page, but that lab has been going for so long,
Yeah.
it felt like I should. All right, any questions at the moment? Because I'm about to start with chapter 6. All right. If that last problem had been in dynamic equilibrium, what would have changed?
The acceleration value would not have been 0.
No, it's still equilibrium, so it's still 0.
But in dynamic equilibrium, it could be moving.
Right.
And if it's moving, well, it would have to be moving at a constant velocity.
Yep.
Right, right. Okay.
Well, if it were moving, then the box is probably like swinging or something, which is probably gonna change the tension on the.
Then it's not in dynamic equilibrium if the box is swinging.
Is there like a ramp that it's sitting on and it's sliding down?
Not changing that problem, all I've done is
It's on-
change one word.
It's on the earth and the earth's spinning, so exactly the same.
It could the entire system just be on a moving surface or platform.
Yeah, so what does it mean to be moving?
Change in position?
Relative to something.
That's a key.
Uh,
So dynamic, if I made a dynamic equilibrium, nothing would have changed at all, other than the fact that, oh, the whole thing is moving at a constant velocity.
not just the box.
Yeah, everything would be moving. So instead of being sitting right here relative to us to be 0, it's now doing this. Unless we moved along with it, and in which case it's still at rest. It's part of the reason why we get the exact same answer, because whether it moves or not depends upon the observer. And my looking at it should not affect the answer. Not to get to quantum physics, does looking make a change. All right, so this is the time I get to throw things. I've never heard a student doing this. I have damaged the periodic table. And there was a potential disaster. About to do centripetal motion, and should I pull the string out of this and see if I can get a better one? We didn't have the rubber stoppers yet, and as people were swinging, the rope broke. But what we were using for what we're swinging around was one of the metal masses over there. And so I was standing right here, and all of a sudden there's this, as one of the metal masses goes flying across and hits the board. No one was hurt. Thank goodness.
Terrified.
There we go. That was a little better. Now, when I was doing the demonstration similar to this last time I taught middle school, and hopefully, again, the last time I ever teach middle school, I did not hit Scott. First period, I got closer to Scott than I intended, but I did not hit Scott. Fourth period rolls around, student comes in, says, "Hey, Dr. Fox, I heard you hit Scott this morning." No, I did not hit Scott. What I do want to do is hit this X right there. And then be standing over here.
I'm sorry.
I can trust that, see? All right. So right now it's tied around my finger, but as I swing it around like this, the question is, where do I need to release it so it hits the X on the board? So for an absolutely spectacular model drawing here, that's the room. There's my X, and there's me with this thing swinging in a circle.
So it would be the point on the circle where the tangent line would be pointing at the X.
So it's somewhere around 230. So release it there.
Yeah.
I'm swinging around like in that direction.
That makes sense to me.
There's general agreement on that?
I have a feeling we'll be proven wrong.
Let's find out. Does anyone have an alternate before we show whether this is right or not?
And maybe just move.